Here's a little heads up. We are about to embark on a mathematical exploration, one without a very particular direction. This video is structured in a way that we'll start with the basics and gradually work our way up to more challenging concepts. We begin by introducing what should be an interesting idea, and then provide context by showing some practical applications of it, before going deeper into some really fascinating connections with other areas of math. If you're already familiar with Pascal's triangle, feel free to skip ahead to this timestamp. Otherwise, stick around for a quick refresher. First, let's play a little game with numbers. Start by writing a 1 on the top. Now, write 2 more 1s on either side underneath. Continue making more rows, where a number is the sum of the numbers above it. This structure could go on forever if you wanted it to, and this is known as Pascal's triangle. What you may or may not realize is that this is actually a table of combination numbers. For example, suppose I have 5 objects. How many ways can I choose 3 of them? You could choose these 3, or these 3, or these 3. Because we don't care about the order, choosing A, B, and C is the same as choosing C, B, and A. In this case, we find that there are 10 different ways to choose 3 from the 5. And so we say that 5 choose 3, usually written like this, is 10. It turns out that there's a formula for this. This exclamation mark refers to the factorial function. If we were to write out all of the values in a table like this and compute the values, we would get Pascal's triangle. I have a whole video covering this in more detail. Link is in the description. What's interesting about Pascal's triangle is how often its numbers appear in places you might not expect. For example, how would you expand x plus y to some power? It turns out that the shortcut lies in these combination numbers. For example, the coefficients of x plus y to the 4th are simply the numbers in the 4th row of Pascal's triangle. So even in algebra and analysis, these numbers will show up. Let's now play around with this structure and uncover some of its hidden secrets. As mentioned in the introduction, Pascal's triangle is a table of combination numbers. Notice that if we label the numbers by their combinatorial definition, the top row is actually row 0, and the first number of each row is element 0. We can pick any values for n and k, and find n choose k in the triangle. Of course, n and k have to be non-negative integers, and k is at most n. But why those conditions? Why can't we do, let's say, 5 choose 6 or -1 choose 1? See, if these values added together equals the sum here, then we can say the sum minus this value must be this value. So, if we pick a group of 3 numbers in this downward-facing triangular arrangement, as long as one of the numbers is missing, we can always determine what that missing number is. Let's call this the addition rule. Let's apply this rule at this location and fill in the missing value. Clearly, it must be 0. We can continue to fill in the other numbers on the outside and see that they are also all zeros. Remember, these are combination numbers, so technically when we take this value, we are asking, if I had 3 objects, how many ways can I choose 4 of them? That's impossible, so there are 0 ways to do this. Similarly, we can't choose -1 objects out of 3 objects, so this value is also 0. In fact, to construct Pascal's triangle, all you need to start with is this infinite row of zeros with the exception of a single 1 somewhere, and the addition rule. This starting row can be thought of as the seed values that allow the structure to emerge. This idea of 1 produces all is very useful, and we will be using it again soon. Okay, so that seems to work. But have you thought about what lies above Pascal's triangle? What lies over here, where we haven't filled in values in that direction? This time, our trick won't work, because whatever we pick, we have 2 missing values, not 1. Even if we start with a single arbitrary seed, we can only fill out that particular row, and then once again, we're stuck. So what do we do now? Let's take a look at this diagonal, which consists of all combination numbers representing n choose 0. That tells us that there is exactly 1 way to choose 0 of the objects, no matter what the number of objects is. So theoretically, this diagonal can continue on. But wait a second, this value represents -1 choose 0. But what even does -1 objects look like? Does it even make sense to pick 0 of them? In the world of math, there's a way to justify this. Consider, for example, n choose 3. Let's write out the formula and simplify. When n factorial is divided by n minus 3 factorial, all of the factors in n minus 3 factorial cancel, leaving us with just n times n minus 1 times n minus 2. We can see that n choose 3 is basically just a degree 3 polynomial. And so, if we can plug negative numbers into the polynomial, we should be able to plug them into the n choose k expression too. And since n choose 0 is the polynomial 1, n choose 0 is always just 1. So now we know that this entire diagonal consists of 1s, we have enough seed values to fill in all of the negative rows of Pascal's triangle. It turns out that this extension is not only justified, it is the most correct or most natural extension of Pascal's triangle, in a particular technical way, but we won't be going too deeply into this idea in this video. And by now, you've probably noticed that in this region, we basically have Pascal's triangle, but rotated, with alternating positive and negative signs. Let's call these the light and dark sides of Pascal's triangle, for convenience. Here's an equation that describes this relationship. It allows us to translate a combination number in the light side into one in the dark side, and vice versa. Now, suppose we want to translate this value here to the dark side. How does this work? Notice that we can draw a line of reflection, such that the light and dark sides are mirrored, as long as we ignore the signs. Each time we increase n on the light side, it is the same as decreasing n on the dark side. Each time we increase k on the light side, we would be increasing both n and k by 1 on the dark side. We can now see that these values line up, so we get that these values are equal. This relationship is an example of what is called combinatorial reciprocity. If you want to learn more, here is a more advanced video on my channel. But we are only just getting started. Let's investigate the relationship between the light and dark sides more. Since the two sides are almost symmetrical, there might be a way to flip them. There are several equivalent ways to swap the light and dark sides. For example, you can mirror the entire triangle along this line, or take every other diagonal and flip all of the signs. But that's not all. There's even a third way by playing more with our addition rule. Remember, the addition rule says that if we have two numbers on top, we add them to get the number below. Let's simplify the representation of this rule with symbols. Suppose the rule here says that a plus b equals c. After rearranging, we get that minus a plus minus b plus c equals 0. Here's the diagram of this rule. The plus and minus signs represent the sign of the value in this equation. This helps us better visualize rule variations. We can rotate the addition rule, changing the direction of the addition. Another way to think about this is to say that the rotated addition rule now looks like a subtraction or difference rule, where we subtract these two numbers on top rather than add them. Now recall that to generate Pascal's triangle, we need these seed values and this addition rule. What happens if we apply this rotated rule instead? As you can see, once we fill in these values, the light and dark sides simply flip, and there we have the third method for flipping. So, what's the point of doing all of this? Well, they're powerful intuition and problem-solving strategies for understanding what's coming next. The key takeaway is this. Number 1. As long as you assume these seed values, the addition rule will automatically generate not only the light side of Pascal's triangle, but the dark side as well. Number 2. You can flip the light and dark sides in several equivalent ways. Number 3. Since subtraction rules are basically just rotated addition rules, they will also produce Pascal's triangle, just maybe in different positions or orientations. Ready for an exercise? I have a sequence here. What comes next? This sequence might look strange initially, since it starts out looking like powers of 2, only to diverge later. It turns out that this is actually a pretty famous sequence. Check out the video linked in the description if you want to learn more about where this sequence comes from. Back to our discussion, here is one way to figure out the answer. Start by subtracting these two values and writing it underneath. Then continue to apply this pattern to the rest of the sequence. This is called a finite difference. Take the finite difference of the next row and continue this process until we get a bunch of zeros. Now, technically, we don't know that this row here is constant, but if we were to simply assume outright that it is, we can now fill in those values and reverse the difference process to find the next values in the sequence. The assumption that any particular row is constant is actually quite essential. Notice that if the problem had arbitrarily given the next number to be, say, 58 instead of 57, we would need to take more finite differences to get to a row that can be assumed constant. Nevertheless, we could still find a valid answer, even though it would be completely different. It turns out that assuming the constant row was where we had it before gives the correct particular sequence we were looking for, but in general this might not be the case, so be careful. If you were me, you'd probably be hoping for a formula to spare us all from this computation by now. Fortunately, there's a trick. By simply collecting these values in the first diagonal as the coefficients, we now have a formula for the sequence in the top row. This is known as the Gregory-Newton formula. As long as the sequence is polynomial, this formula will work, since the combination numbers here are polynomials. To derive this formula, rather than proving that we can obtain the formula from the sequence, let's simply prove that the formula produces the sequence. To demonstrate that this strategy is valid, we need to show that the same table of differences can be produced from either 1, by using the sequence as seed values, or 2, by using the first diagonal as seed values. Because the process of applying addition or subtraction rules is reversible, we will always get the same values no matter which method we use. Before we continue, let's talk about the concept of adding or superimposing tables together. Let's first look at what will happen if we add two tables together. Take any table that follows the addition rule, could be Pascal's triangle itself, or any table that is generated from different seed values. Now take another such table and superimpose these tables together, and sum the corresponding values. You will see that the resulting table still adheres to the addition rule. The proof is simple. Consider these general values. Take the corresponding sums, and we see that if the addition rule works on the initial tables, then the rule also works on the sum. This is true no matter where in the table we start from, so it is true universally. Now let's return to the problem of finding a formula for our sequence. Let's see what happens if we assume the only non-zero value in the initial diagonal is this 1. Since our difference rule is simply a rotated addition rule, we can now treat the 1 as a seed for generating the rest of the table. When we do this, Pascal's triangle appears. The values in this first row can therefore be described by this expression. Similarly, we can do this for any single 1 value in this first diagonal. So if there are a bunch of non-zero values in this diagonal, all we need to do is superimpose these tables together. In this case, all of our coefficients are 1. But even if they weren't, we can simply multiply all of the values in the table by a constant. This produces a formula that describes the sequence, so this proves that the formula works. Notice that some sequences go both ways, as they could be indexed with negative numbers. Suppose you only had the negative side. How would we find a formula now? For now, let's also just consider positive n indices. We'll flip them back negative later. Let's do the same thing we did before. Start by only having a single 1. Then apply the subtraction rule, and once again, we find Pascal's triangle. But be careful, this time with alternating signs. We take several of these, superimpose them like we did before, and we have a formula. Again, remember that this time we have alternating signs. Finally, to convert our index back to the negatives, let's just flip n. So we have found two formulas for the same sequence, and so we know that they are equivalent. However, do notice that they use different values in the table. The first formula uses the values in this diagonal, while the second uses values in this diagonal. You might wonder, why did the dark side of Pascal's triangle appear on the other side? Well, we need two things to produce Pascal's triangle: a set of seed values and an addition rule. One of our core assumptions is that this entire row is constant, and that we only have a single one in this diagonal, with everything else being 0. If we rotate our grid so that the addition rule is facing downwards, we notice that this is just Pascal's triangle. By now, it should feel as natural to consider the dark side of Pascal's triangle as the light side, as we've seen that getting formulas and relationships to work in either direction requires both sides. This approach is very powerful for solving many problems, as we will see in the upcoming sections. Now that we have a general feel for Pascal's triangle and the gregory-newton formula, we are finally ready to apply what we learned to some common combinatorial identities and see how they work. If you're not familiar with combinatorial identities, don't be intimidated. All it is an identity involving combination numbers. Let's take a look at this simple example. Suppose this is our n choose k. Here is n choose k minus 1, and here is n plus 1 choose k. This identity says that summing up these two values would get us this, and this is simply the addition rule. We call this Pascal's identity because it is the rule that generates Pascal's triangle. Here is another one. This one simply says that if you start on a 1 and begin summing all the terms in a diagonal, then the sum is the next number here, one row lower and one step in the opposite direction. The proof is simple. Rotate Pascal's triangle on its side, then treat this row as the top row. Since the second row is the finite difference of the first row is the sum of the second row. You could even apply the gregory-newton formula on this if you want. And we have now proven our result. This is commonly referred to as the hockey stick identity because of the shape it makes. Now let's look at a more challenging identity. Imagine I take these two combination numbers and multiply them, then shift the k numbers of each of them in opposite directions and multiply them as well. Keep going and then sum all of these products across an entire row. The result is simply the sum of these two top values choose the sum of these two bottom values. And so this value here can be generalized. To prove this, simply decide that this value here is where our sequence starts, at n equals 0. This forms a sequence along the diagonal here, which we can plug into our gregory-newton formula, and that gives another way to express the sequence, and we are done. Here, our initial row was row 2, but we could have used any row. Fully generalized, the identity says this. This is called Vandermon's identity. While the gregory-newton formula is powerful enough to prove the examples we've seen, and at least one more we will see later, each of these identities each have many different proofs, all elegant and important in their own way. I highly recommend checking out those as well, because they will connect other important concepts that this method will not be able to. What other combinatorial identities can you find? Another interesting point to mention is that almost all combinatorial identities that hold in the light side also hold in the dark side. However, some can still break down. The most notable one is probably this. This identity is saying that because the light side of Pascal's triangle is symmetrical, for example, these two values are equal. However, this doesn't hold in the dark side. Here's what the formula would be when translated to the dark side. Investigating the dark side of Pascal's triangle enabled us to gain deeper insight into discrete math. But we will go even further. Now we will apply the concepts of Pascal's triangle to an area most people would not expect to have much relation to discrete math: calculus, by doing calculus almost entirely using discrete math. First, I want to introduce some special notation. When we take the derivative of f, we write it instead as df. You can think of d as a function that takes a function as input and outputs another function. This kind of function of functions is called an operator. Here, our derivative operator d also happens to be a linear operator. There are two properties that a linear operator must satisfy. First, if you multiply a scalar to either the input or output, it's the same either way. Second, you can distribute the operator over addition. Let's now define what we call the forward difference operator, denoted as delta, to form our finite differences. This is also a linear operator. It turns out that there are a lot of interesting properties that these two operators share. Going back to our finite difference table, we can see that if we start with a sequence of degree n, each time we take a finite difference, the degree goes down by 1. In addition, if the leading coefficient is 1, then the constant in the constant row is n factorial. This mirrors what happens with derivatives. You can see that the same process also applies there. The reason is simple. Recall that n choose k can be written as a polynomial. If we do this, then the polynomial has degree k. For instance, n choose 3 equals this, which means it is a degree 3 polynomial. The gregory-newton formula tells us that the highest degree term would be of degree k, and that the finite differences would go down k rows before hitting zeros. Another way to understand forward differences from a calculus perspective is to think about the forward difference as the slope of a secant line. Suppose this is a graph of our f of x. Let x be this c constant. This means f of c is the height here, and f of c plus 1 would be this height here. If we draw a line between these 2 points and try to find the slope, we get the forward difference. The derivative is almost the exact same idea, except it is the result we get when the gap between the points of the secant line approaches 0. These are not quite the same, but hopefully you can see how they are very similar. The derivative, as we know, is the slope of the tangent line, and the forward difference gives us the slope of the secant line. Let's look at another example of this parallel. Start with the sequence 2 to the power of n. Take a finite difference, and we get the exact same row. This means that the forward difference of 2 to the n is 2 to the n, similar to how the derivative of e to the x is e to the x. This also leads to another cool idea. If we apply the gregory-newton formula to this, going off to infinity, we get this identity, which says that the sum of a row of Pascal's triangle is a power of 2. However, now we run into a problem. The coefficients we need to collect go on forever, resulting in an infinite sum. Is this even allowed? While this seems to work for the light side, the sum of a row on the dark side of Pascal's triangle seems to diverge. So how do we even know that this identity is true? To understand what's going on, we will need to investigate further. Some of you may recall that functions like e to the x have what is called a Taylor series, which is a power series that can be used to evaluate the function. You can think of it as an infinite polynomial, and the more terms you calculate, the more accurate it is. This is the Taylor series for e to the x, centered at x equals 0. If we start plotting more and more terms, we can see that the function starts to converge towards e to the x, little by little. We can take initial segments of our sum for 2 to the x and do the same, treating the combination numbers as polynomials. We can once again see that it approaches the function little by little. And so, under some technical conditions, you can actually use the infinite variant of the gregory-newton formula, specifically if it converges to the function. So as we can see here, the function converges nicely for positive x values. However, for negative x values, these approximations flip back and forth wildly. This is also why these row sums in the dark side of Pascal's triangle diverge. But don't worry, By embracing the dark side and flipping Pascal's triangle, we will eventually find ways to get around this. For now, the question is, if 2 to the n can be written as an infinite sum, could we do this with any other functions? Let's see what happens when we try it on something more exotic, like sine of x. This time, because our inputs are in radians, all of these sequence values are very ugly irrational real values. But if we ignore that ugliness, muscle through and find the finite differences, then collect the coefficients to find a formula, we can now plot it, and find that it does in fact converge towards sine of x. Compare this to the Taylor series, and you can see that the Taylor series will center around x equals 0. But our forward difference formula becomes more accurate to the right. This is called the forward Newton series. But now we have another small issue. How can we find these ugly coefficients here more efficiently? To solve this, all we have to do is apply the same idea as we did in the previous section, only this time seed the top row. For example, let's suppose we are trying to find a formula for this coefficient here. Now put only a single one in the top row. Compute the differences. Now we simply multiply the sequence value here that is actually here, in this case sine of 0. Do this process with all of the other sine values in the sequence, then superimpose all of them together. Notice that the structure that forms when we seed the top row with a 1 is the dark side of Pascal's triangle, so we can actually generalize these numbers. Now the true values of the diagonal are exposed, and we can write their exact form in terms of the function. Here is what they look like for sine of x, and in general for an arbitrary function f of x. So now if we plug these into the Gregory-Newton formula, we have that the general form of our forward Newton series would be this. Compare this to the Taylor series of a function. Pretty slick, right? And this formula has a lot of practical use as well. Recall that we can take any initial segment of a sequence and find a formula for it. But the sequence can be extended arbitrarily. What this tells us is that there are really an infinite number of functions that can pass through any finite number of fixed points. Using a particular method, such as the Gregory-Newton formula, to select a particular function to try to fit a set of points is called interpolation. In this case, our formula allows us to take n evenly spaced points and find an n-1 degree polynomial that fits it, such that it is exactly correct at the n fixed points. So each time we give it an extra point, we can increase the degree of the polynomial approximation by 1 while correctly maintaining the existing function values. And so it shouldn't be too surprising that most functions that have a Taylor series have a forward Newton series representation. To understand why we would choose the forward Newton series over a Taylor series, consider what kind of information is needed to build these series. For our forward Newton series, all we needed are n consecutive terms of the sequence. For the Taylor series, you would need the first n derivatives of the function at some point, which in many cases could be much more complicated to find or even define. We could, alternatively, use the analogous forward difference values at 0 for the forward Newton series, but in most cases we will have the function values. We'll compute the forward differences for the Gregory-Newton formula anyways. All this time, we have been calling this the forward Newton series because we've been using the forward difference operator. There is also a backward Newton series using the backward difference operator as well. We can use the same techniques to derive the dark side of the Gregory-Newton formula, and then extend it infinitely. We use the same method of seeding the top row to find a formula for the diagonal coefficients. And combine them and see that our backward Newton series would look like this. Compare this with the forward Newton series formulas. Now let's take a look at what approximations for sine of x would look like using all of these series. Compare the forward Newton series, Taylor series, and backward Newton series. Notice that the forward Newton series gets better as you travel to the right, because of the values we are interpolating over, and so the backward Newton series goes to the left, compared to the Taylor series, which stays centered. We can finally answer the question we put aside a while ago. How can we use the dark side of Pascal's triangle to fix the divergent negative side of the forward Newton series for 2 to the x? Let's now find the backward Newton series for 2 to the x instead of the forward series. Write out the sequence as usual, collect the coefficients, and notice that they are simply decreasing powers of 2. Plug them into our backward-facing Gregory-Newton formula, and we have our backward Newton series for 2 to the x. Let's now plot the different series of 2 to the x to compare. This is why the 2 to the x approximation is so poor with the forward series. The function grows very aggressively, making it impossible for the negative domain to stay close to 0. On the other hand, if you use the backward Newton series to get the negative side close to 0 first, then the positive side will naturally grow out, and the process converges to the function everywhere. In the previous section, we showed a lot of parallels between the two types of calculus, one using classic calculus, working with continuous domains, and the other using discrete methods, working in discrete domains. We can think of finite differences as being analogous to derivatives in many ways. Since the inverse of the derivative is the integral, and the inverse of the finite difference is just a summation, we can also analogously think about summations as integrals. If both classic calculus and discrete calculus methods can extract the essence of a function through a power series, then shouldn't there be a more direct link connecting them? It turns out there is, using a linear operator. Let's call it phi as a placeholder. For now, just follow the big picture, and I'll explain what phi is and what's happening behind the scenes later. Let's say that you want to find a formula for the summation of k squared. Using this phi operator, we can send this problem from the discrete world over to the continuous world. Once it is in the continuous world, we can now take the analogous operation, the integral, and then just apply phi inverse, sending it back to our discrete world. And we get our answer. Quite magical, isn't it? We can draw a transition diagram here, with our different functions and the different operators that convert them from one another. And so by simply following the diagram, any problems involving differences in summations can be solved using derivatives and integrals, and vice versa. Well, as long as there's a power series that converges to the function. Okay, so what is this magic phi operator? To understand it better, we need a bit of setup. Firstly, we need to understand functions as infinite dimensional vectors. This shouldn't be too intimidating because we've actually already done this. There are lots of ways to represent functions as a vector. For example, write a function as its Taylor series, the infinite polynomial. Collect its coefficients, and those values are the values of the vector. And this is why the function has to have a power series that converges to the function. Otherwise, the power series wouldn't represent the function, defeating the purpose, which doesn't help us. But now we have a small issue. If the functions are now vectors, how do we take their derivatives or differences? Simple. We just treat a linear operator as an infinite dimensional matrix. For example, this is the matrix of a derivative. If we have a polynomial like this, then this is our vector. Multiply the matrix with it, and you will see that each row produces the derivative of that term. The final result is our derivative. Similarly, here is the matrix for the finite difference. Once again, we can examine what the values of one column would be by writing out the definition, then collecting the coefficients. Remember that when you expand a binomial to a power, the coefficients make a row of Pascal's triangle, but since we subtract the leading term, the first one is missing. Here is the matrix for integrals. There is a matrix for summations, but it's pretty difficult to derive naively, so let's say for now that we don't know it. By the time we are done, you'll be able to derive it fairly easily. Now that we understand functions as vectors and linear operators as matrices, we can now present phi and its inverse, which will also motivate the better names we will give them. Phi and inverse phi look like this, where the numbers inside are called Stirling numbers. Let's go back to the example where we found the summation for k squared. Remember our strategy. We first send it to the continuous world, then take the integral, then send it back to the discrete world. Here is the vector for n squared. Multiply by the phi operator, and we get this vector. Then take the integral using this matrix here. Finally, multiply inverse phi to send it back to the discrete space. And voila, we have our answer. However, there are still a few mysteries left unsolved. What are these Stirling numbers and how do you compute them? Why does this work? It's time to expose the underlying black magic. Let's first figure out what's happening under the hood, and that will lead us to what the Stirling numbers are and why it works. To begin, let's introduce some notation. This looks a lot like a simple x to some exponent n, but this underline here indicates that we want what is called a falling factorial. What that means is rather than multiply n factors, all of which are x, we will multiply n factors which follow the pattern x, x minus 1, x minus 2, etc. Similarly, we can define the rising factorial, where we multiply x times x plus 1, x plus 2, etc. until there are n factors. These falling factorials might seem familiar to you, if you recall that combination numbers can be written as polynomials. If you write out x choose n, you'll get this, where the numerator is simply the falling factorial, giving us this identity here. To get rising factorials instead of falling factorials, we need to utilize minus x choose n. Remember that we can justify this by thinking about the combination numbers as polynomials. First we write out x choose n, then substitute minus x into the polynomial. We can pull out a minus 1 factor from every factor in the numerator. What is left over is the rising factorial divided by n factorial. Just to clean it up, we can move the sign to the other side. Here are our combinatorial identities involving rising and falling factorials. To get a more intuitive feel for why we are doing this, let's write our Newton series in terms of these rising and falling factorials instead of combination numbers. You can see how they align even more naturally with the Taylor series by analogy. Recall the power rule for derivatives. If we instead use the forward difference on the falling factorial, we will get a very similar looking rule. The proof is straightforward if you just pull out common factors, but you can also derive it from Pascal's identity, our addition rule. Subtract this term on both sides. This left side is now just a finite difference, so we can rewrite it with our forward difference operator. Rewrite each side in terms of falling factorials, and finally, multiply both sides by n factorial. The backward difference gives us a similar power rule involving the rising factorial, and we can prove them in the same way, but this time we will have to use the dark side of Pascal's triangle. We will proceed with our proof of the power rule similarly. Pull out the negative value up here, rearrange a bit. Now the entire side here is a backward difference. Multiply both sides by minus 1 to the power of n minus 1. Rewrite in terms of rising factorials, and finally multiply by n factorial. And so, we have two different power rules for rising and falling factorials, derived from the dark and light sides of Pascal's triangle. So what is this operator doing? It's simply rewriting a polynomial that is written in terms of falling factorials into one in terms of powers x to the power of n. If we recall the transition diagram we made, and write out the steps that go around like this, we can locate our magic step here, where we sent the function into continuous derivative world. What is really happening is that we are simply rewriting the function in terms of powers and applying the derivative, which looks like and acts like the forward difference operator. This operator, in the language of linear algebra, is simply a change of basis, and in that new basis, the forward difference is the same as the derivative in the old basis. So now we know how the magic works. How do we write powers in terms of falling factorials or vice versa? Firstly, the most naive way of converting falling factorials into powers is to simply distribute. If we do a couple of these, then collect the coefficients, this gives us one set of the Stirling numbers, called the Stirling numbers of the first kind. Since these have alternating signs, we call them signed Stirling numbers of the first kind. We eventually need the inverse too, as we also need to know how to convert falling factorials back into powers. Finding the inverse is trickier, as it would require you to solve a system of equations, but would give us the other set, Stirling numbers of the second kind. Since all of the values here are positive, we call these unsigned Stirling numbers of the second kind. But is there an easier way to find these values? The distribution is very ugly for higher values of n, and calculating the inverse by solving a system is even more tedious. Recall that for Pascal's triangle, we have our addition rule, Pascal's identity, which tells us that the sum of two adjacent numbers gives us the number underneath it. Stirling numbers of the first and second kind have very similar looking recurrence rules. Notice that one of them has an n factor and the other has a k factor. These recurrence relations are much simpler to work with because you don't need to solve linear systems. All you need to do is plug and chug, just like how you would build the next row of Pascal's triangle. Let's do a quick recap of what we just covered so far. We now know that our magic linear operator is actually just a matrix. The way this linear operator works is by converting powers x to the power of n into falling factorials and vice versa, as a change of basis. And so the derivative and forward difference behave the same in their respective bases, thanks to similar looking power rules. This tells us how the values in the matrix are obtained, and these numbers are called Stirling numbers. On top of that, although we have a naive way of computing them, we do have a much faster and easier recurrence relation. All that's missing now is to prove that these recurrence relations actually work. I find that an algebraic or inductive proof here, although quick to present, is very dry and doesn't feel particularly interesting, so I want to use a combinatorial proof. It requires more setup, but it is very elegant and interesting. I will separate it out into a supplement video for those who are curious. Do you want to know what Stirling numbers count? Watch that video and you'll find the answer. We already showed that we can convert from powers to falling factorials using unsigned Stirling numbers of the second kind, and can convert them back using signed Stirling numbers of the first kind. Did you notice how we didn't mention rising factorials yet? It turns out that similarly, you can use signed Stirling numbers of the second kind to convert powers to rising factorials, and unsigned Stirling numbers of the first kind to convert back into powers. Note that in both sets of signed Stirling numbers, the alternating signs are assigned in the exact same way. This gives us two slightly different transition diagrams, depending on whether we are using a forward difference or a backward difference. This also means that the inverse of each of these differences, these sums here, are slightly different. If we let s of n be our sum here, notice that the backward difference gives us the term being summed. If we change this upper limit from n to n minus 1, then the forward difference gives us the term being summed. That's the main difference between these two summations. Alright, now we are ready to try a few more examples. They really shouldn't be too bad now that we have the big picture. Let's try to find the derivative of this function using finite differences. We can actually use either forward or backward differences here, so let's pick to use forward differences, which means we will once again use this transition diagram. We start here, and our goal is to get here. Let's go the long way around. First, convert to the discrete domain using signed Stirling numbers of the first kind. Now we can take the forward difference. Finally, send it back to the continuous world using unsigned Stirling numbers of the second kind. As expected, we get the derivative. Here are the steps using magic, and here is what is happening under the hood. So far, the two examples we have already done are pretty mild, in the sense that we are making an already easy problem more complicated. They were more for demonstration purposes, as it's easier to verify and follow what exactly we were doing. It's time to now throw these techniques at a harder problem, solving for the summation of a polynomial. Many math students would probably recall learning these formulas in school, usually with the first three memorized. Let's try finding this sum here, the sum of k to the fourth. First, notice that if we treat the sum as a function, we need to take the backward difference in order to obtain n to the fourth. It's time to use the other transition diagram. We start here, and here is our goal. Unlike the other examples, we don't know an easy way to directly jump to this goal, so we actually need to go around this time. Transform this into the continuous domain using signed Stirling numbers of the second kind, take the integral, then transform back with unsigned Stirling numbers of the first kind. And we're done. Think about what we just did. We just solved a discrete math problem using calculus. This field of study, where we use identities that look like the power rule in order to do what looks like calculus on them, is called Umbral calculus. We have merely done an introduction here, where we present three of the most basic examples of such power rules. There is a lot more that can be done with what we learned here today that has applications and connections to other fields. This video is already long enough, so we'll just stop here for now. It's time to recap and map out our journey from start to finish. We learned that Pascal's triangle is a very important mathematical structure that contains combination numbers. By viewing combination numbers as polynomials and making some natural assumptions, we can select seed values that, in combination with the addition rule, give us the negative rows of Pascal's triangle, which we call the dark side. Addition rules, like what we have here, and subtraction rules, like the one we used in our finite differences, are really one and the same. They will both extend naturally to produce Pascal's triangle, both the light and dark sides. By superimposing tables that follow these rules together, we can find a polynomial formula for any sequence we want, where if we are given the first n terms, we can find a polynomial formula of degree n-1 using the Gregory-Newton formula. Thanks to the dark side of Pascal's triangle, we not only have simple ways to compute the coefficients along the diagonal, we can even interpolate backwards. Understanding the existence of both the light and dark sides and using this formula, we can visually intuit many combinatorial identities. And so by studying finite differences, we can see that they behave in many ways like derivatives, and this allows us to find connections to calculus. By extending the Gregory-Newton formula infinitely, we can even find alternate series representations of functions, in terms of falling or rising factorials rather than powers like the Taylor series does. We can treat certain functions under some conditions as infinite polynomials, specifically when they converge to the function, which allows us to understand functions as vectors and linear operators like the forward difference and the derivative as matrices. This gives us an easy way to convert the polynomial bases using Stirling numbers to falling and rising factorials. This means that all problems involving derivatives and integrals can be rewritten in terms of finite differences and summations and vice versa. In this way, we are introduced to novel ways of approaching calculus. This produces a very discrete computational method for solving calculus problems. These ideas are very closely related to the concept of analytic functions. We didn't go over this in the video, but analytic functions and analytic continuation are an incredibly important concept. In future follow-up videos, the different examples of series we went over today will serve as great examples for understanding deeper ideas in this area. I think it's a good time to talk about why I chose this topic for this year. Usually, in public education, at least in the United States, a lot of emphasis is placed on calculus and analysis, and not as much on discrete math. I hope this video will provide a new perspective on how useful and important discrete math can be. The direct analog between discrete math and calculus shows that there is a wide range of discrete math applications that can help build and shape our intuition. As humans, we tend to make all kinds of assumptions and associations about the identity of something, such as thinking that combination numbers can only describe how we count objects, that discrete math only involves discrete objects, or that functions and vectors are entirely unrelated structures. However, like any subject, math is an interconnected web of ideas, and only through keeping an open mind and exploring will you be able to uncover some of its mysteries. Accepting what lies at the heart of an idea, rather than its superficial appearance, not only helps us grasp it more fully, but also reveals how rich and interwoven everything truly is. A final note is that I have linked many relevant resources in the description, including references to some of the things we discussed, filling in some foundational understanding, or topics for further exploration. A poster of the diagram in the conclusion can be found in the description as well. If you like my work and want to see more, please like, share the video, and subscribe to my channel. And if there is anything in particular you would like to request from me, please check out my AbleBees profile, where you can petition me to make a video on a topic of your choice, and you and others can support me by pledging to a petition. For instance, would you like me to make a video showing why Taylor series work by using these analogous finite differences? Then come contribute to the petition. There's also no risk to you, because your pledge won't be processed unless I deliver the content. Thanks for sharing this very long journey with me, and I hope to see you all again next time.